our selected site is in the lowest bracket of New York, with fewer than 0.3 crimes per 1,000 residents. The site is located in somewhat of a transportation hub, with access to numerous subway lines and a bus station directly across the street. Walking paths were added around the building and by the river, enhancing the work environment and improving the design score on the LEED checklist. The site also has several bike racks around the building. Porous pavement was used in the parking lot to help prevent stormwater runoff, as well as reduce the urban heat island effect. The building footprint is located on the northern end of the site near the river. This building location was chosen to maximize the southern exposure, daylighting, and to ensure that it would not be in the shadow of the existing buildings and trees on site. The building orientation was tilted slightly off of an east-west orientation to maximize solar gain and create an intimate entrance area. The north side of the building utilizes an infill wall of CMU masonry with a tan brick veneer rain screen. This reduces noise pollution from the bridge, as well as provides a drastic increase in insulation. The green roof construction and implementation of the specified double-paned, low emissivity fixed windows also helps reduce loads and the environmental impact. The PV louver system will not only reduce cooling loads and contribute to energy consumption, but also acts as a rain screen and protects the facade. The riverside location offers advantages beyond the aesthetic appeal by allowing accessibility for a closed-loop renewable river water heat exchange for the HVAC systems. A variable refrigerant flow system was selected for the open office, conference and meeting rooms, and human resource areas. This system exchanges energy with the closed-loop river exchange and uses refrigerant as the heating and cooling medium throughout the building. It is highly efficient, operating at variable speeds and sharing energy internally within spaces. This is also a renovation-friendly system, since only small refrigerant lines need to be fit in the ceiling space as opposed to bulky ductwork with traditional systems. Individual heat pumps were selected for the R&D and computer server spaces. These units also use the river exchange and distribute air at required temperatures and rates to maintain specific pressure requirements. Several energy models were created to analyze how our design changes affect the building's energy savings and environmental impact. The energy modeling iteration graph shows how the heating and cooling loads were reduced with each design change that was made. The base model shows the loads for the existing building that was given to us. The following iterations encompass changes to the building orientation, outdoor air requirements, specific occupancy scheduling, the new floor plan, energy-efficient lighting alternatives, shading from the photovoltaic louvers, and efficient windows. This final iteration includes all design changes and determines our post-renovation load calculations. These changes, although mainly passive, produced drastic changes to the previously calculated baseline energy model, reducing the cooling load by almost 40%. The new loads were determined for each room, zone, and system. Using these new load values, specific systems for each zone of the building were selected and sized accordingly. After implementing our new systems into the energy model, the energy consumption pre- and post-renovation was compared. The energy consumption of the building was drastically reduced through our renovation design. The annual consumption of over a million kilowatt hours dropped to around 320,000 kilowatt hours. The monthly comparison shows that in the hottest months of the year, the energy consumption is dropped substantially due to the efficient HVAC systems and building orientation and shading. The energy distribution of our building is broken down into categories of HVAC, lighting, plug loads, the computer server space, and miscellaneous. A cost-benefit analysis was performed to determine the renovation payback. The lifetime cost comparison chart shows that initially, a traditional variable air volume system is less expensive and cheaper in repairs and maintenance costs. However, the new design pays back after year 12, and at year 40, the efficient system will have a net cost of around $1 million less than the baseline system.